Hi everyone. In this lesson, we will study some of the applications of derivatives. And we have already looked at some of that, such as velocity, average rate of change, instantaneous rate of change in section 1.3. But there, the techniques we were using were very long. It relied on creating a table or the extensive limit definition formula. So here we're going to take advantage of the shortcut rules. And one of the most typical example you will see in this section is when they give you the distance function, say y equals s of t, which represents distance from the ground at any given time t. And if we want to get the velocity function from that, all we have to do is take the derivative of the distance function, the rate of change of distance per unit change in time. That will give us the velocity function. And something we haven't discussed previously, but we're going to also take a look at in this section, is the second derivative of the distance function, s double prime. And that is also the same as the first derivative of velocity. And that represents the acceleration. So in other words, acceleration is the rate of change of velocity, how velocity changes over time. And so we're going to use both of these equations in the examples that follow. And also a few tips here to solve the examples, just very typical types of examples, like they might ask you, when does the object reach its maximum height? In that situation, typically we're going to find when velocity is equal to 0. So let's say this is the graph of y equals s of t. So let's say the x-axis represents t and the y-axis represents s of t. So if you find a point where the tangent line is horizontal, basically that's where the slope of the tangent line is 0, typically that's where the maximum height will be reached. So that's a little tip. Anytime you hear the word maximum height, think about setting the velocity function or the first derivative of distance equal to 0. But on the other hand, if they ask you, when does the object hit the ground? In that situation, you want to know where the distance from the ground is 0. And for that, you should set the distance equation equal to 0. So to find out when does it reach maximum height, we set the derivative equal to 0. To find when does it hit the ground, we set the original function, the distance function, equal to 0, because at that point, distance from the ground should be equal to 0. Okay, so let's take a look at a few examples. So here we have equation for the distance from the ground. This is represented distance of an object thrown up in the air on the surface of the moon. And it's given as s of t equals 24t minus 0.8 t squared meters in t seconds. So the rock thrown vertically up on the surface of the moon will reach that height of s of t meters in t seconds. First, they want to know what are the functions that represent the velocity and acceleration. Okay, that should be easy. So velocity is simply the derivative of the distance function, s prime of t. So one by one, I'm going to take the derivative. We worked with the variable of x before, but dealing with t is the same idea, right? So just treat t as your variable. So derivative of 24t will be 24, and derivative of negative 0.8 t squared. So bring the 2 down. 2 times 0.8 is 1.6, so it will be minus 1.6 t. So this is our velocity equation. And for the acceleration, now take the derivative of the velocity, rate of change of velocity. The first one will be 0. Derivative of negative 1.6 t will be negative 1.6. Now, the given units for s of t was in meters and times in seconds. So the velocity will be in terms of meter per second, and acceleration will be in terms of meter per second square. Part B is asking us, find the height and velocity 1 second after the object was thrown in the air. So now that we have our equations, so we already knew the distance from the ground. The height equation is s of t. Basically, we're asked to find what this s of t when t equals 1. And next, we're going to do the same thing. We know what v of t is, and we're going to need to find what happens 1 second later, so v of 1. So plug in 1 for t in the s of t equation, and plug in 1 for t in the velocity equation. So let's do that, going back to s of t equation. 24 times 1 minus 0.8 times 1 squared, which is 24 minus 0.8. So that'll be 23.2 meters. So 1 second later, the object is 23.2 meters from the ground. And V of 1, so now let's go to this equation. 24 minus 1.6 times t, t is 1. So that one will be 24 minus 1.6, and that's 22.4 meters per second. So 1 second after the object was thrown in the air, its distance from the ground is 23.2 meters, and it's moving at a rate of positive 22.4 meters per second. Part C asks us to find when the object reaches its maximum height. So this is when I mentioned to you that it helps to know that little trick to find when the object reaches the maximum height. So we think of the graph as an upside down parabola, because remember, the given s of t is a quadratic function that has a negative coefficient of t squared, so we know it's going to be an upside down parabola. And when t is 0, s of t is 0, I know it goes to the point 0, 0, right? So that's why I can do a rough graph over here. So to see when it reaches maximum height, we need to set the derivative of the distance function equal to 0. So, and then that way we're going to figure out when that maximum height is reached. So s prime of t is the same as velocity, so set the velocity equation equal to 0. So 24 minus 1.6 t equals to 0, therefore 24 equals 1.6 t, and t equals 24 divided by 1.6. And we can plug it into our calculators if there need be, and we're going to get t equals 15 seconds. Okay, so that only tells us part of the story. So it reaches the maximum height at 15 seconds, but the next question is, what is the maximum height? So we know this occurs at the point of t equals 15, but we also want to know the height at that moment in time. What was the maximum height reached by this object? So to determine that, now that we know it occurs at the moment of t equals 15, let's plug that into the original equation of s of t. So let's find s of 15 to find the maximum height, which is the height at that moment in time. So we're going to find s of 15, going back to the original equation, which was 24t minus 0.8 t squared. And everywhere I see t, I substitute in 15. So I have now 24 times 15 minus 0.8 times 15 squared. And again, we can simplify it on the calculator, and we shall get 180, and the units are meters. So what we're saying is this maximum height that it will reach will be 180, and at the point of 15 seconds after it was thrown in the air. And I'd like to show you what that looks like on Desmos calculator. So you can just go to desmos.com, and on the first equation there you can enter y of t or s of t equals and enter your equation. And it gave me something. I had to play a little bit with the window over here, like I had to change some of the values, or you can zoom in and zoom out to get something reasonable. And because we got 180, I knew that for my y-axis, like I had to go at least to 200, 300, you know, to be able to include 180. Otherwise, it'll be just chopped off the top of it. You're not going to be able to see. Okay. So again, we can also verify here that approximately at that point, you see when I clicked on it, it's occurring at the ordered pair 15, 180. So at time equals 15, height equals 180. And that's when the maximum height is reached. Okay, so let's take a look at the next question. When does the object reach the ground? Okay, so for this one, we know the distance from the ground will be 0 at that moment. So we want to find when does this point occur. So at that moment, we know s of t will be equal to 0. Now, some of you might say, well, let's use symmetry because it reaches maximum height at 15, so it will probably hit the ground at 30 seconds, right? But I want you to be prepared for questions of this type. Sometimes they're not hit from the ground level, maybe something like this. So you see, like the time it takes to go to maximum height will be shorter than the time then later on to hit the ground after that point, and it's not going to be symmetrical. So let's learn how to do this the correct way, and then if you can notice that it's perfectly symmetrical, you can also use that idea to check your answers, but it's not always going to be symmetrical. So let me then set S of t equal to 0 to find out when the object hits the ground, and remembering that S of t was 24t minus 0.8t squared. Luckily, this is only 2 terms. It's very easy to factor. Just take out the t. So we have t times quantity 24 minus 0.8t equals 0. So either t has to be 0 or the other factor. So let me set the other factor, 24 minus 0.8t equal to 0. And when we solve for t in that equation, we're going to get t equals 24 divided by 0.8. And just like we expected, that should be 30. That is indeed 30. So for this question, we could guess that again, but this technique will work even when it's not a perfect symmetrical situation. And what about part F? What is the velocity of the object as it reaches the ground? Now, 1 second after point of impact, of course, the velocity is 0. The object comes to a start, assuming it doesn't bounce back, etc. But literally the moment before impact, like maybe a split second, 1/100th of a second, even just before it touches the ground, it's coming down with a velocity. So what is that velocity? That's the question. So we want the velocity at the moment it hits the ground, so at 30 seconds, it's coming down with a velocity. And we go back to our velocity equation, which was 24 minus 1.6t, and t is 30. So if we simplify that, we should get negative 24 meters per second. And the negative represents the fact that it's going downwards at that point. So when it's going upwards, the velocity was positive. When it's going downwards, velocity is negative. And if you just take a look over there, at the moment of impact, if you draw the line, the tangent line at that point, what type of a slope would that tangent line have? Positive or negative? Negative, right? So, and remember that velocity is basically the slope of the tangent line, right? Because it's s prime of t, the slope of the tangent line of the distance function. So it turns out to be negative 24 meters per second. And of course, you can verify many of these things by doing it on the Desmos or using your graphing calculator. You can check the point of impact, you can check the maximum height, and when it reaches the maximum height. Okay, let's take a look at one more example, but I think I'm going to put this in the next segment.